or three different samples, like three different categories for the age groups. And I was wondering what method we should use for that because we didn't learn how to compare three populations. We only learned how to compare two. So would we do like the H test, which like I read off the textbook, or
I mean
um,
the second question
yeah.
about the breathlessness.
Mhm.
It's a chi-square test. I don't know if you have covered that.
Oh, okay, yeah, we did.
It's a chi-square test, so basically it's a test for independence, a chi-square test. Um, so
And
basically the result, like after chi-square test, you can draw two conclusions, either one, right? First, the illness is not related to the ages. Or the second conclusion would be the illness is related to correlated with the ages. So basically that test cannot give you like other from t-test from z-test you have a very clear conclusion about for example my sample mean is different from zero, or in a t-test my sample mean is different from another sample mean. But here the purpose of a chi-square test is to see if two random variables are correlated with each other. So that's the purpose of a chi-square test. So basically, when you conduct a chi-square test, first you need to do such assumption that those two variables are independent,
okay,
right? And in the question two, for example, let's see. The- So first we have a chart. Like this chart is just our observations. But then we need to have a hypothetical chart that is our expectation if those two variables are independent. And then we compare those two charts and to see if there's huge difference that lead to reject the assumption of independence. Right, so now I look at this chart, I don't know if there's any correlation between breathlessness and ages. So first I assume, okay, those two random variables are independent. So then I have to calculate my expectations and guess a professor gave you some formulas during the class, but to understand those formula, basically um, you see the total number of yes of illness is 2,221. The total number of less than 29 years old is 3,743. And the total observation, which you can observe in the bottom right, is 18,282. Right, so how to play around with those numbers, assume independent. We know if two random variables are independent, then the probability of those two both happening is just the probability of the first one happening times the probability of the second one happening. And here, by the same token, here's two statement is first, I have this illness, and the second one is I am less than 29 years old. What is the probability that I have this illness? It's just 48 divided by 2,221. That's the probability from this sample I observed. And then what's the probability of being 29 years old or less? Is 48 divided by 3,743, right? And I got those two probabilities separately. And then under my assumption of independence, what is the probability of I am both illness and under 29 years old? You just times those two probabilities together and you get a new probability, which is your expected probability of both have the symptom of breathlessness and under 29 years old. That's the probability, and then you times the total observation, which is 18,282 that gives you the expected number, and that expected number would probably different from 48. But then how huge is that difference? You have to use the formula during the class. I guess you need to difference it and square it and then divide it by your observation, something that is your chi-square distribution. You need to sum up all of those difference and to see if that number is huge or not. If that is too
So,
large, you would say my assumption doesn't hold, and those two variables are actually dependent on each other.
so could you do that for any age group? Like, could I just do that with 30 to 49 and compare it
Yes,
to
definitely. And
612?
you have to do everything. You have to do everyone.
Oh, you have to do it for each age group?
Yes. For example,
Okay.
there's like overlapping on yes column and less than 29 column. Then the overlap is 48, right? But then there is some overlap between like maybe no column and 50 plus. And then you find the overlap, the observation is 3,415, but also you need to calculate what's your expected number of people under the assumption of independence. Then you sum them
So
up.
you do 3 separate chi-square tests then?
This is one chi-square test, and those are just like sub-step of a chi-square test.
Okay, so would the null hypothesis be uh, the expected number of illnesses based on
Null
the
hypothesis would
probabilities?
be like those two variables are independent. The likelihood of getting a symptom of breathlessness and my age are independent of each other. That's my null hypothesis.
Okay. Also, like, how do you know that this is a chi-squared, like off the hat, like just by looking at this? Like, I couldn't really see that immediately.
When you want to understand if two variables are dependent with each other, like intuitively, I guess you would assume the older people, they have a higher probability of some breath issue, right?
Mhm.
So actually, intuitively, there's some kind of relationship between the ages and this illness. Um, that's something you want to study. Like, is there really a relationship? Right? If you look at the question 2A, it asks, do you think the incidence of breathlessness among the coal miners depend on their age? There is like one variable depend on another variable. That is a chi-square test. And the null
Okay.
hypothesis is always those two variables are not independent.
Okay. Um, okay. And also for question one, uh, for the test statistic, would you use the one with the z-score?
Share the screen. Here it is. You mean part A or part B?
Oh yeah, for part B, for the Wilcoxon test,
Actually,
because
I had that slide. Maybe have that slide.
it was like, this is a work I did. I don't know if you
Slide.
see, like that was my
Yeah.
test
So
statistic.
basically, a Wilcoxon rank test is so first you have to list all those numbers and
Yeah,
sorting them, right?
yeah.
To have them ranked. Uh, yes, here's some formulas on Wilcoxon rank test. So the expected number of A, I think I should reshare this one. Here is the expected number of A, right? And then the variance of A. So I talk about the first one, the expected number of A. So basically, you have multiple numbers. Actually, you have two groups, and you rank them. And maybe the group A has the rank of 5 and 6, and then group B have a rank of 4 and 7, right? With the same
Mhm.
mean, right? So some people scored number 1, and another person scored number 10. And then we
Okay.
have another two persons scored number 5 and number 6. I want to compare those two groups. Like how to compare that using the ranks. That's a question I have. Um,
Okay, so you just do T1 minus the expected or EW over the square root of the variance.
yes, that is the z-score test. That's something you need to do. But first you have to calculate what is the expected number of A and the variance of A. This A and B, it's interchangeable. You can choose either group, and that gives you the same answer. But first you have to choose a group, and then you calculate the expected ranks and the variance associated with that rank.
Okay.
Basically, if it's if it is a strict equal sample size, right? If sample A and sample B have exactly the same observation, then my expected number, the expected rank of A, would be you sum up all the ranks and divide it by 2. That is my expected ranks. But sometimes the sample size are not equal. So basically those formulas did some like adjustment in case of the number in sample A and the number in sample B are not equal. And you can use this formula to calculate the expected number. So and intuitively, if sample A contains more numbers, contains more observations, where sample B only has several numbers, then the expected number of A in a fair situation would be much higher than B. And this formula basically adjusts the difference in number of observations.
So this is like universal, regardless of.
Yes, yes,
Oh, but don't NA and NB have to be greater than 10 for this formula to work?
true. It's just like a weighted average.
Okay. Okay. Yeah, I think that's it for my questions.
Sure.
Yeah, I'll let the other students ask. All right, thank you.
Mine. Bye.
Oh, you just said that you're gonna go over the linear regression, right?
Yeah, I will go over the linear regression.
Before we do the linear regression, can I ask a question about the homework?
Sure.
So for like number one, I know that we're gonna do a two-tailed test, but what is like the alpha? Like, are we just assuming it's 0.05 for sorry, for 1A, like where we had to find
Yes,
the
yes.
t-test.
Actually, like point 0.025. So basically, you have the
0.025,
default
okay.
alpha. The default alpha would be 5%, and then you're doing a two-tail test. So
Yeah, so
in
it's
each
divided by
tail,
2.
it's like 2.5%. Yes.
And then do we have to show like a graph, like the curve with
Not,
the like two tails?
not really, but basically, if you graph it, like it help you to understand like when to reject the null hypothesis, because a lot of times you see sometimes people are confused with um, when the critical number, when the, for example, the t critical number is greater than
Uh-huh.
the t we should reject or fail to reject, and vice versa. So basically, if you have a bell curve kind of thing, and you can draw in that picture, it helps you understand like in which region you're gonna reject the null hypothesis, but it's not required.
Okay. Wait, could you just, what is a critical value again? Is that the like t with the like the 0.025?
Yes, you have your number of observation,
Mm-hmm.
which is n, and then you have your alpha, and you go to the table, you can get a number, a t value.
Okay, yeah, the t
that would be
table.
your t critical value.
And we're comparing the critical value to what exactly to prove or reject the null hypothesis?
With the test statistics, right? With all those numbers, you're gonna find a t value by yourself. That t is your test statistics, and you compare your t with the t critical value, right?
So the t that we find from the two tests or from the two samples, then we like compare it to the critical value.
Yep.
That we find from the table.
Yep. But that's one way. So basically, there's two ways. So first, it's what I said. You first you find your own t score, and then you find the t critical value from the table. Then you compare your t with the t critical value, and if your t is greater than the t critical value, then you're going to reject the null hypothesis. That's the first method. And secondly, basically it's pretty similar, but just saying it in two ways. Like after you find your own t, right, you can have your t and the number of observation or the degrees of freedom. Actually in the chart you have to know the degrees of freedom, which is n-1 or n-2 for two sample, and you have the degrees of freedom, you have your own t, then in the table you can get an alpha, right? And then you compare that probability. You don't get an alpha, I'm sorry, you get a p-value, that is a probability. And then you compare that probability with alpha that you have chosen. So basically it's a question of like there's A, B, and C, which is degrees of freedom, p-value, and t. And every time if you find two, you can go to the table and get a third variable. And basically it doesn't matter which two you find, but as long as you find two, you can get another one.
Okay, so then for the homework, which method do you recommend
It doesn't
doing?
mind. It doesn't matter because it's not difficult. Like all of them are easy as long as you find two, variables. Anyhow, you have to go to the table and get the third one.
Okay, and then could you explain what the Wilcoxon rank sum test is?
It's a test about ranks, right?
No, not how we're supposed to apply it in the question. Because it says can you answer the question? Can you answer the question in A using the Wilcoxon rank sum test?
Right. So basically, first you have to go to the course slides. I think you have covered the Wilcoxon rank test, the formula about that test. So you have to review the class slides, and then basically you're gonna rank all those numbers, the Devon and the Cornwall. You have to rank all those numbers, and then your new data set would not be 170, 111, 135, etc. But instead it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It's just their ranks, their relative ranks. You don't care about the absolute value anymore. You just rank them and you get their ranks. And then you have a test about those ranks. You'll find all the ranks of Devon or all the ranks of Cornwall. And actually, I have those two formulas here, but you have to go to the course slides and find
Yeah,
those
I'm looking at the
formulas,
course slides right now.
Yeah, those are some formulas about that. And actually, the test statistics would be a z-score. So basically, you have the expected, you need to calculate the expected rank of Cornwall, for example, and then the variance of the ranks of Cornwall. And if you remember, a z-score test is just the expected number minus what's your observed or null hypothesis divided by standard deviation. That is your z-score, right?
Okay, so then when we're doing the Wilcoxon sign test, we have to do both the test statistic and the reference distribution, like with the variances and everything, or are we just picking one of them, one of the two methods?
There's only one method, but two groups. You just need to pick one group. Like
Okay, yeah,
either
that's what I meant.
A or B. Here in the slides, it said WA, but in the context of the homework, it's the Devon versus Cornwall. You just pick one, and you get the same results.
Oh, okay, so you just apply the rank test to one of the groups.
No, you have to rank them, right? You have to compare those two groups, right? Your standard method is a two-sample t-test, right? When you want to compare A with B, you have to use all the numbers in A and in B, right? That's the default, that you have to do that. Or you only use numbers in A, why don't you compare A with C, compare A with D, right? You have to use all the numbers in A and in B, and you rank all those numbers. But
Okay.
then when you find the ranks 1, 2, 3, 4, 5, 6, you don't have to find the ranks for both groups, but instead you find one group would suffice.
Okay. Okay, that makes sense. And then for 2, are we just doing another 2-sample t-test?
You do a chi-square test. I have
Okay.
some explanation with another boy, like during the first 5 or 6 minutes in this office hours, and you can watch the recordings about that. It's a chi-square test. It's not very difficult, but really important. So I'm gonna review some course slides.
Okay, and then what you went over with the kid, is that like just like a general example or specific to the homework?
I don't know about your homework on regression yet. I guess you don't have a regression about you don't have a homework about regression, but you will have soon, and that's very important. So,
No, I meant I thought you just said the example you went over like in the beginning of the office hours was
okay. Oh, that's
about the chi-squared.
yeah, the question 2.
Yeah, but is that like, because I missed that part, is that like in relation to, is that just like an example of chi-square?
The same question. Go over the
Okay.
same question.
Okay, and then do you go over 2B as well?
I didn't go over 2B, but that question is less relevant. As long as you finish 2A, I guess you can write about something in 2B. It's not very hard.
Oh, so that's more of a it's like a written response.
Yeah, it's more like an interpretation of what you have found in 2A.
Okay. Okay, that's fine. That's all my questions then. Thank you.
True.
我以为你要讲那个 linear regression。
现在讲的。